Hi class, welcome to the next section, chapter 10.7. We're going to discuss partial fractions. For now, this is the last section of chapter 10. At some point in time, I may add another 2 sections to chapter 10, but for now, and for the foreseeable future, this is the last section, okay? Partial fractions are pretty important. It's one of the I'm not going to say one of the main applications, but it's something that I use quite often actually when I'm teaching. It's also used quite often in a lot of higher level courses. So basically what partial fractions is, obviously we'll get into it quite in depth in a second, but as an overview, basically what partial fractions is a way to take a fraction, a rational function really, rational expression, and break it down into parts. Okay, so when we first started talking about rational expressions, a polynomial over another polynomial, our goal was to take maybe 2 of those things or 3 of those things and add them together or subtract them from each other, okay, and combine them into a single rational expression. So what we're doing today is we're actually doing the opposite. We're breaking it down into its pieces. So you might say, well, why is that useful? It comes up quite often actually in much higher level classes, such as differential equations. You will see it in calculus. It kind of just pops up everywhere. I use partial fractions a lot when I'm trying to make up problems, right? Like if I'm trying to make a nice problem where I want things to cancel nicely, when I have you guys add or subtract 2 rational expressions, I use a partial fraction decomposition, okay? So that's me personally, but again, there's many uses for these things. It's a very important tool as this comes up as you're going through your upper level math courses in physics and engineering. So again, partial fractions is basically a method of separating our rational expression into a sum of smaller rational expressions, okay? So we're thinking about it as undoing the addition of these things. So we're not just subtracting things, right? We're breaking them down to its parts. So the whole process is called, again, partial fraction decomposition. So let's assume that we have a rational function. Our rational function we're going to call r, okay? The numerator function is p of x. The denominator function is q of x. What we really want to do is we want to take q and we want to break it down into its factors, okay? So we're not going to cover, but we're going to use a lot of what we did in chapter 3 for polynomials, where we use the rational zeros theorem, synthetic division, that kind of stuff to factor our polynomial. So whatever our polynomial is for q, that's the one we want to factor. We do not care about factoring p. We do not care if we can simplify p over q by canceling common factors in the numerator and denominator. We don't care about any of that. What we care about is the factors of q. That's what really drives the partial fraction decomposition. So we want to factor out q as much as possible. And when we factor, we're not going all the way like we did in chapter 3, where we would go all the way down to the radical or the irrational zeros, the irrational factors, and the complex factors. We don't have to go that far. We're really focused on factoring over the integers. Okay, so we're really trying to break it down into the integer components, the integer factors. We can have the rational ones in there too, but we really want to have them in an ax plus b sort of form. Okay, so this brings us to 4 cases, right? As we factor things, there's really 4 cases that come about that we want to consider for partial fraction decomp. First is that when I factor out q, every single factor is distinct, meaning there is no multiplicities, okay? There's no multiplicity. There's no x squared as a factor. There's no x plus 1 squared, right? Where x plus 1 times x plus 1 is a double factor basically. So we don't have any multiplicities. That's the first case. That's actually the easiest case. That's the nicest case to work with, is when all the factors of q are distinct, okay? The second case is that there is multiplicity in these factors, okay? So all of the factors are not distinct, but all the factors are linear, okay? And also for Q, for the first case, that's also what we're interested in. It's linear factors. And when we say linear, we mean binomial factors. Okay. None of the factors have a higher degree than 1. So it's like x plus 1, x minus 3, x plus 5. They're all different, and they're all linear at most. Highest degree is 1. Second case is that we have multiplicity, but everything is still linear. Okay. The third case is that we have some quadratic factors in our denominator. Okay. But they're all, there's no multiplicities of that either, right? So possibly there's a quadratic there that we cannot factor anymore. So again, it's prime over the integers up to a quadratic amount. And the fourth and last case is that we have a quadratic factor that has multiplicity. It's a repeated factor on the denominator, and it appears more than once. Okay, so those are our 4 cases that we need to discuss. It's not so much that one is easier than the other, but when we're building this decomposition, the first one is the one that we like the most. Okay, when it happens. So we can have a case where all 4 of these things are present, and that's fine. We just deal with them as they show up. Okay, so let's talk about case 1, when all of the factors are linear. Okay, degree is at most 1, or is equal to 1, I should say, and there is no multiplicities in our factor. So if I could take the denominator and I can factor it in this form, so some number times x plus a constant times some other number times x plus another constant, so forth, where all of these numbers are distinct. So the 0 here is not the same as the zeros here, is not as the same as the next 0, and so forth, right? Then I can take my rational expression, my rational function here, and I can break it into parts in the form of a constant on top. This is not a matrix. I know we've been dealing with capitals as matrices, but for right now, this is just a number. A1 is a number, A2 is a number, and so forth. So we'll have some number over the first linear factor, plus some number over the second linear factor, plus some number over the third linear factor, and so forth, until we run out of linear factors, distinct linear factors, I should say. So that's the first form of the decomposition. The second case is when we have a multiplicity. Okay, so let's say that it's a multiplicity of k, though maybe that's like x plus 1 squared, right? So maybe something shows up twice, or maybe the factor breaks down to x plus 1 cubed, right? It doesn't really matter what the value is, but if we do have multiplicity, then for that single factor that is a multiplicity k, our decomposition breaks down to a number over that factor, right? So notice that a1x plus b1 is a1 and b1, a1 and b1. It's the same factor over and over again. So for the first term, it's some number over that factor plus some number over that factor squared plus some number over that factor cubed plus some number over that factor to the 4th power, and so forth, up until whatever that multiplicity is. So if it has a multiplicity of 2, you would only write it twice, right? You would only go up this far. If it had a multiplicity of 3, you would have an a3 over that factor cubed, right? So you're kind of building yourself up to the multiplicity when there's multiplicity. So these two methods, these two cases, really just repeat themselves for case 3 and case 4 when we have quadratic factors. Okay, so case 3 is that you have a prime quadratic factor or multiple of them, right? So if q of x can be factored and there exists a quadratic factor that's prime in the denominator, then for that factor, you write it as ax plus b over ax squared plus bx plus c. If there are 2 of them and they are both distinct, I would have another one, so it would be plus dx plus e, because I can't use these same values, so dx plus e over whatever that quadratic factor is, and then another and another. So just like we had here in case 1, where we had distinct linear factors, and each time this was a different value, it would just do the same thing, but on the denominator it would be quadratics, and the form for the numerator is not just a single value, but a linear value, right? Ax plus b. So the next one would be dx plus e, and then fx plus g, hx plus I, or however you want to use those values. So the fourth case is that we have a prime quadratic factor, and there is multiplicity. So that quadratic factor has a multiplicity of k. Okay, it looks like the following. So again, the expansion is still there, but it repeats. Okay, so same form as we had before. So I just have new ones, and that multiplicity just keeps on increasing by a factor until it's multiplicity of k, like I said before. So the process. Okay, so this is all very abstract. It's very formulaic at this point. We'll have a couple of examples, and the examples will show you like, oh, okay, this is the way it's done, right? It makes a little more sense, obviously, when you see an example. So let's talk about the process. So for the process is, first and foremost, I have to factor q. Okay, that's the first thing, because I need to know what the factors of q are. The factors of q is what drives this partial fraction decomposition. Once I have my factors of q, I look at each case. It could be possible that I have to use every single one of these cases in my decomposition. When I break down q, it's not going to be all case 1 and all case 2 and all case 3 and all case 4 for one problem, right? It's not like, oh, I've done this one problem and this problem is only case 1. It's possible, but it's not always the case, right? So what happens is I have to look at each factor independently and say, okay, do I have a case 2 and a case 3, or is it a case 1 and a case 3, right? Maybe all of the linear factors are distinct and there's one quadratic factor. Well, then that means I have a case 1 situation and a case 3 situation, right? Maybe I have multiplicity in my linear factor, okay? So I have to use case 2. Maybe I have other factors that are different from this one that has multiplicity, so I have to use case 1. And maybe I also have quadratic factors in there that are prime and there's no multiplicity, so I have to use case 1, 2, and 3 in my one problem. So I'm looking at all of every single factor and saying, okay, is there multiplicity here? Is it distinct? Is it quadratic? Is there multiplicity for the quadratic or the linear? And depending on each factor, it depends on how I form my decomposition. Okay. So again, I'm going to rewrite R of x based on the factors that are present. Okay. I'm going to clear denominators. I've been talking about clearing denominators this entire video series. So if you're still not clear on what clearing denominators are, I suggest you go back to chapter 1 and refresh on that. Remember, anytime there's an equal sign and we have fractions, we can get rid of our fractions, right? We're just going to multiply the entire equation. Every single term in the equation gets multiplied by the LCM, or the lowest common denominator. Okay? And when we do that, all of the fractions should go away, basically. Right? Then what we're going to do is we're going to form a set of equalities, right? If I have some x squares present, I'm going to say all the x squares on the left side are equal to the number of x squares I have on the right side. For my x's, the number of x's I have on the left side is going to equal the expression I have for x's only on the right side. For constants on the left side is going to equal the expression I have for constants on the right side. So I'm going to form a bunch of equalities which actually will create a system of equations for me. Okay? And so then I solve the system of equations that I get out with the methods I've learned in this chapter. I can use Cramer's rule, I can use inverses, I can use reduced row echelon form by turning it into an augmented matrix. There's a few things we have on our belt at this point, and I would use whichever ones are the most appropriate or whichever ones I find is the easiest to use. Okay. After I do that, for the answers I found from solving my systems, I will replace these unknown values, these A1s, B1s, B2s, whatever it is that I have, from my number 2 step in this process where I was rewriting my expression based on the factors that I have. Okay, so let's go ahead and do an example. Okay, so let's find the partial fraction decomposition of 2x plus 1 over x squared plus 3x plus 2. So again, the first thing I want to do, I want to factor q. Obviously, the p, the numerator, is not factorable anyways, but even if it was, I would not factor it, okay? So this actually factors really, really nicely. I chose a nice easy example for the first one. We know there should be x plus 1, x plus 2, okay? So we take this, and it factors to x plus 2 times x plus 1 over 2x plus 1. So my factors here are linear, and they are distinct. They are not the same, and there's no quadratics or anything like that. So my decomposition then is very, very easy, very straightforward. I can rewrite this as some number over the first factor plus some number over the second factor. The only time things are different is when there's multiplicity here or if there's quadratics. Okay, so this is pretty much the standard manner of doing this. If I had a x plus 1 squared, for instance, I would have a third term of c over x plus 1 squared, because I would need to build this one up one power at a time to whatever that multiplicity was, but that's not the case, so I don't have to worry about it. Okay. Now I'm going to clear denominators. So I'm really looking at just these two. Okay, this is my right side, this is my left side, because dealing with it in this non-factored form is not helpful, so I'm going to really just focus on this and this. I multiply by the LCM, or this factored form here, it's already the LCM actually. So I'm going to multiply the numerator by x plus 2 times x plus 1, which will cancel these. I'm going to multiply this times x plus 2 times x plus 1, and the x plus 2's are going to cancel, and I'll be left with x plus 1 times a. Here I'm going to multiply it by the same thing as well, and the x plus 1's will cancel, and I'll be left with an x plus 2 on top. Okay, so 2x plus 1 will leave me with a times x plus 1, because the x plus 2's cancel when I multiply everything times this denominator, and I will be left with b times x plus 2 for the second half. Okay, there's no more fractions. Very standard, straightforward equation. I need to distribute my a and distribute my b. Okay, so I have ax plus a and bx plus 2b, and that equals 2x plus 1. So now I'm going to equate the variables that I have on the left side with the variables I have on the right side. So my x's are ax and bx. If I add those together, it has to equal 2x's. My constants are a and 2b, so if I add those two constants together, it has to equal 1. Okay, so equating my x's gives me 2x is the same as this x plus this x. My 1 has to equal my other two constants. Now, there's two ways to think of this. I'm really only interested in a and b here, so I can get rid of x. Another way to think about it is, if I take this first equation and divide everything by x, well, there's no more x's, and I just know that a plus b is 2. Okay, so I don't need the x's here. So this is going to give me a system of equations of 1, 1, 1, 2, 1, 1, 1, 2, and that's going to equal 2, 1. So from here, I can solve by reduced row echelon form. I can solve by using the inverse of 1, 1, 1, 2. I can solve by Cramer's rule, right? So here I'm going to turn it into a matrix. I'm going to find this inverse. I'm calling it V because I don't want to call this A, because I already have A somewhere. So I didn't want to confuse you guys and say A inverse, and then you're like, oh, well, A is here. It's not a matrix. This is number. So I'm calling it V. So this 1, 1, 1, 2, I'm just calling it V. For right now, it's temporary, right? I have to give it a name. So the inverse of this matrix is 1 over, this is 2 minus 1. Okay. Remember, these two swap positions, and these two swap signs. So that's 1 over 1. So 2 negative 1, 1, 1 is my inverse. I take that and I multiply it times 2, 1 to solve for my a's and b's, which in this case I'm calling x. Okay. So I'm going to multiply that times 2, 1. So that'll be 4 minus 1. So the first value will be 3. So a is 3. And this is negative 2 plus 1. So that's a negative 1. Okay. So a is 3. Okay. That's a is 3. B is negative 1. And so I come back here and I just put them in place. So I have 2x plus 1 over x squared plus 3x plus 2. That is the same as 3 over x plus 2, sorry, minus 1 over x plus 1. So If I were to give you guys a problem at the beginning of the semester where I'm like, hey, simplify this rational expression, I know that if you take this term and subtract this term, this is the number you should get out. Okay, you should get out this as an expression. So we're taking this and we're breaking it down into sum of two parts where the denominators of those parts are made of the factors of this common denominator. So that's partial fraction decomp. That's the first example. This was a very, very easy, basic example. Now, if I was a great professor, I would do a medium level example, but I'm not, so I'm going to do a hard example. But this next example will give you a nice overview of what happens when you have a nice mixture of different factors. Normally when that happens, however, it gives us a really, really big system of equations to solve, so it gets very time consuming to do that by hand. So let's just go ahead and look at that. We're going to kind of take some shortcuts here though, so that this video isn't like hella long, right? So let's find the partial fraction decomp of this following problem. So again, this numerator, I don't care about it. Well, I do care about it, but I don't want to factor it, right? That's not my goal. So I'm going to take this denominator here and I'm going to factor it. Now, at the beginning of the semester or the beginning of this video series, you should have looked at this and been like, what the hell is that? I don't know how to do that. But at this point, you should be like, I know what to do. So we're going to find the possible zeros, rational zeros, and then we use our rational zeros theorem, right? Our synthetic division, and we break this down into its factors. And once we know what the factors are, then we can get started with the partial fraction decomp. Okay, so let's look for the possible zeros. So we have 4 over 1. So remember, we use the positive and negatives. So remember, this is factor, this is numerator. Factors of this is the denominator. So we have plus or minus 4. We'll have plus or minus 2, plus or minus 1. Okay, so those are the factors of 4. This one doesn't really offer anything, so we don't have to worry about any fractions. Remember, we always try to choose plus or minus 1 first and see what we can get. So we'll start with x equals 1. So that means we have negative 1 in our little, we use, when it's x equals 1, we do use 1 here. Okay, but the factor will be x minus 1. So using the decomp, we know we start with 0. I'm not going to go super slow through this because we've already done it. So remember, we start with 0. We add it together. That result we multiply, right? So when we come and we finish this out, we should end up with 0. So add these together, multiply, add, multiply, add, multiply, add, multiply, add, multiply, add, and we get 0 out. Okay, so we have one factor. One factor is x minus 1. We try this one again and again and again until it fails. Okay, so I tried again. It doesn't work. So x minus 1 is a factor only once because the second time around I didn't get my answer. So I can break this down to x minus 1. This is my remaining polynomial, okay, not this thing here where it failed. So I have my x, 4, 4x, 9, 10, constant of 4. So I'm going to go here, instead of using 1 again, because I know it doesn't work, I'll use x equals negative 1. Okay. Go through the process. Okay. Again, I'm going faster here because we had a whole chapter on this thing, so you guys should remember how to do this. Negative 1 works. Okay. Again, start with 0, add, multiply, add, multiply, add, multiply, add, multiply. Okay. So I got 0. So I have another factor. Try it again, and it works again. Try it one more time, and it doesn't work. Okay. I didn't. Well, actually, maybe it does work, but the thing is I have, I'm down to a quadratic, right? So I found 1, 2, worked again. My answer is a quadratic. I can just use regular methods once I get down to quadratic, okay? Notice that this is prime, right? So the factors of 4 that add up to 2, there are none, right? Unless I had a negative there, which I don't. All right. So again, notice that this is not factorable. Okay, so I can break this down all the way into its factors. So notice I have one distinct factor, one factor of multiplicity, and one quadratic factor. So in this case, I tried to give you one that has a mixture of things to show that that's kind of what happens when we factor, right? We know this from factoring large polynomials. So I have the distinct case, I have the building up to this factor case and I have the quadratic prime factor case. So I'm going to have a mixture of things when I write my decomp out. Okay, so the prime factor gets a single one. Okay, the factor of multiplicity builds up to its multiplicity. So I have one with a single power, and then I have one with the square factor, power, because that's a multiplicity. And then my quadratic factor has an x in the numerator, right? So my unknowns are a, b, c, d, and e. Right? So from here, I need to clear out the denominators. Again, the factored form is nice for this, which is another reason why we want to use it, because I'm going to multiply the entire equation, each term. Okay, remember, each term does not mean top and bottom. That means the piece as a whole, as separated by these plus signs, right? So when I multiply this term by the denominator, it cancels out, right? When I multiply this times the denominator, the only thing that's going to cancel is this x minus 1. So I will have a times everything else. For b, the only thing that cancels is x plus 1. So I'll have an x minus 1. I'll have the extra x plus 1, because only one of them cancels, and the quadratic factor. For the second term, both of the x plus 1 squares, x plus 1s cancel, I should say. And so c will be multiplied times x minus 1 and the quadratic. And for this term, when I multiply it times this denominator, the quadratic will cancel, and I'll just have the x minus 1 and this multiplicity here. Okay. So what does this look like? It's going to be very long. It's going to kind of wrap around to the next lines. So a will be multiplied by this. So again, the only thing that cancels is the x minus 1. Everything else gets written. I will have plus b, where only one of the x plus 1s cancel. So I still have the other one. Okay. For c, the x plus 1s both cancel. So I have x minus 1 in the quadratic. And for the last term, I will have everything but the quadratic term. Oh, I was able to fit it on here. So from here, guess what, guys? We got to actually expand this out, okay? Meaning I have to expand this and multiply it times everything here. I got to multiply this all out. I got to multiply this all out. So we all know how to do that. So I'm going to kind of fast track through that a little bit. I don't have to go slow through this expansion because we've done that tons and tons and tons of times, okay? I got to expand this all the way out and distribute my b across. And I got to multiply this out, distribute my c across, and multiply this across so that I know what terms I have for d and e. So for a, it ends up looking like this. So when I multiply this all out and distribute my a, this is what all my a's look like. I have ax to the 4, 4ax cubes, 9ax squared, 10ax, and 4a for the constants. For my b's, it'll look like this, okay? And you should double check this. Okay, never take my word because I do make mistakes, although I'm pretty sure I did it right. And then my c's will look like this once I multiply this out and simplify everything. And my d's will look like this from this expansion, and my e's will look like this from my expansion as well. So I have all my a's, all my b's, all my c's, all my d's. So now I have to write the equalities. Notice, however, on the left-hand side, there are no x4s. There are no x cubes, but I do have x squares and 3 and x's and 1s. So that means that when I find my collection of x4s, that doesn't mean there is none of them. That just means that if I add ax to the 4 plus bx4 plus dx to the 4, it equals 0. So basically a plus b plus d has to add up to 0. Okay, so again, setting up my coefficients is going to give me the following. So starting with constants in this case, let's come here. I got 4a minus 4b minus 4c minus e. Okay, that's all my constant, has to equal 1. Next I go to my x's. So starting from here, I got 10a minus 2b plus 2c minus e. All right, so you see here I pulled out the x, but in reality we don't even have to write x. We just need to equate the coefficients. Okay, because if I divide this whole equation by x, there's no x's there. So I'm really just interested in negative 3 is equal to 10a minus 2b plus 2c minus e. Right? For my x squares, same thing. These are all of my x squares terms. grouped together. So here I'm just being nice and showing we can pull this out as a factor. Okay, for my x cubes, they have to add up to 0 because there are no x cubes here. And for my x to the fourth, there's no x to the fourth here. So a plus b plus d has to be 0. Okay. Turn this into a system of equations. And I have a very large system, right? I have 5 equations and 1, 2, 3, 4, 5. So this is square. I can use inverses here. Although, again, finding an inverse for a large matrix can be time consuming. Remember, the process for that is we write a partitioned matrix, A on one side, I on the other, and we simplify our A down to I using Gauss-Jordan, and we'll end up with A inverse on the right side, right? So if you go back a couple of sections to inverses of matrices, we can use that. You can use the Cramer's rule using determinants, but that can be time consuming on a large matrix. We saw for a 4x4 it can be a pain in the butt, even more so for a 5x5 unless you simplify. But if you're going to simplify anyways, you might as well use the Gauss-Jordan elimination. So really whatever method you want to use. I'm not going to go through the process of it actually in this case because we've gone through that in other sections. I just kind of used some technology, right? My calculator, basically, there's some shortcuts to do this. I'm not going to tell you what they are, but you can figure them out. So if we go ahead and use a couple of shortcuts, use some technology in order to find this, we can find that our solution to the system is the following, right? So I just reduce it down to reduced row echelon form, and then gives me my my A, B, C, D, and E right away. Obviously, these are not very nice numbers, which is okay. We just deal with them, okay? So I put my A over its factor, my B over its term, right? My C over its term, and my D and E over its term. And you might say, well, dang, Professor Williams, that's ugly. That's fine, right? We need to simplify. Never leave me a fraction inside of a fraction. That means that there's more work to do, okay? This denominator, you can think about as dividing denominators. You can think about this as multiplying by the reciprocal of the bottom term. And that's really not really necessary. These are multiples. This denominator here will just move to the bottom. So just move these denominators to multiples of the denominator. So it really just looks like this, right? The 9 moves down. Here I did have to bump up by a factor of 3 to make this a common denominator of 9. So I can put a denominator of 9 on the bottom. And this is fine. You don't have to multiply things in. You don't have to expand anything. This would be the answer I'm looking for. Notice when I have minuses, I apply the minus signs. Here there's a minus for both, so I had to put it in front because when I do add this together, it gets distributed to the numerator. So just remember that that's the way that works. All right. See you guys for chapter 11. When we talk about conic sections, it could be a little difficult, but the more practice obviously makes things easier. Conic sections to me are pretty interesting, so I'll see you guys for chapter 11 video series.